Now let us look into another way of characterizing the systems, that is stability. Here we will be talking of the stability in BIBO sense, means bounded input and bounded output sense. We say that a system is stable if, means a system is stable in BIBO sense if any bounded input given to the input produces bounded output. Otherwise, we say that the system is unstable. So, for a continuous time system, if mod of x of t is less than or equal to bx, where bx is finite, so this condition implies the input is bounded. If we are able to prove that mod of y of t is less than or equal to by, where by is finite, then we say that the system is stable. Similarly, in case of discrete time systems, the equivalent relation can be written as if mod of x of n is less than or equal to bx, then it implies that mod of y of n, if it implies that mod of y of n is less than or equal to by, then the discrete time system is also stable. Here the quantities bx and by are finite. Now let us consider this by an example. Let us consider a system y of n is equal to x of n minus x of n minus 1. We have to find if the system is stable in BIBO sense. Suppose the input is bounded, it means that mod of x of n is less than or equal to bx, where bx is finite. This is true for every n. Now we have to find mod of y of n. This can be written as mod of x of n minus x of n minus 1. Also, we know that this is less than or equal to mod xn minus mod of x of n minus 1. Sorry, this is less than or equal to mod xn plus minus of mod xn minus 1. Now we know that mod xn is less than or equal to bx, so this can further be written as bx plus, as x of n minus 1 is less than or equal to bx, minus x of n minus 1, sorry, as mod of x of n minus 1 is less than or equal to bx, minus mod of x of n minus 1 will also be, I'm sorry, so here we know that mod of x of n minus 1 is less than or equal to bx. So mod of minus x of n minus 1 will also be less than or equal to bx. So we can write that this is less than or equal to bx plus bx. This is less than or equal to 2bx. As bx is finite, 2bx is also finite. From this we see that mod of y of n is also bounded. From this we see that for a bounded input we are getting a bounded output. Therefore, the system is stable in BIBO sense. Now let us consider a system y of t is equal to 2 times x of t plus 3. Suppose the input is bounded, that is mod of x of t is less than or equal to bx. This is for every t. Then mod of y of t can be written as mod of 2 into x of t plus 3. We know that this is less than or equal to mod of 2 times mod xt plus 3. So this is less than or equal to 2 times bx plus 3. As bx is finite, 2bx plus 3 is also finite. So for a bounded input, we are getting a bounded output. Therefore, system is stable in BIBO sense. Now let us consider a system y of t is equal to integral minus infinity to t x of tau d tau. Now we have to find if the system is stable in BIBO sense. Now we know that the input is bounded, that is mod of x of t is less than or equal to bx for every t. So mod of y of t can be written as mod of integral minus infinity to t x of tau d tau. This is less than or equal to integral minus infinity to t mod of x of tau d tau. because this is from the relation um, mod of a plus b is less than or equal to mod a plus mod b, and integration is analogous to summation. So we know that mod of x of tau is less than or equal to bx. So this can be written as less than or equal to integral minus infinity to tau bx d tau. We know that the summation is from minus infinity to t. So this quantity tends to infinity. From this we see that for bounded input the output is not bounded, that is mod of y of t tends to infinity. From this we see that the system is not stable in VIBO sense. There is a discrete time system given as y of n is equal to x of n multiplied by x of n minus 1 plus 2. Check if the system is stable in BIBO sense. For checking the BIBO stability, first assume that the input is bounded. So mod of xn is less than or equal to bx, where bx is finite. We have to prove that for mod of y of n is also bounded. So to check that, we know that mod of y of n is equal to mod of x of n multiplied by x of n minus 1 plus 2. This is less than or equal to mod xn multiplied by mod x of n minus 1 plus 2. As the system is stable, as the input is bounded, this is equal to bx square, sorry, this is less than or equal to bx square plus 2, which is finite as bx is finite. Therefore we see that for a bounded input the output is also bounded. From this we see that the system is stable in BIBO sense. Now let us consider another system, which is a continuous time system whose input output relation is given as y of t is equal to t square into x of t. We have to check if this system is stable in BIBO sense. If the input is bounded, we know that mod of x of t is less than or equal to bx. From this, we can find that mod of y of t is equal to t square multiplied by mod of x of t, which is less than or equal to t square into bx. From this, we see that as t tends to infinity, we can just mod of y of t can also tend to infinity in BIBO sense. From this, we see that for a bounded input, the output need not be bounded. Therefore, the system is not BIBO stable. Now, let us consider another system whose input output relation is given as y of t is equal to f of integral minus infinity to t x of t dt, where f of x is equal to 1 for x greater than or equal to 1. It is minus 1 for x less than or equal to minus 1, otherwise it is 0. We have to check if the system is stable in BIBO sense. So for a bounded input, it means that mod of x of t is less than or equal to bx. The output can be given as mod of y of t, which is equal to mod of f of integral minus infinity to t x of t dt, as even as f is a cliff function, we know that mod of y of t is always less than or equal to 1. This is because f is a cliff function, so the output values of f will always be in minus 1 to 1. So mod of y of t is less than or equal to 1. From this we see that the system is BIBO stable. Now let us consider another system which is given as y of t is equal to mod of x of t. We have to find if the system is stable in BIBO sense. Suppose the input is bounded, that is mod of x of t is less than or equal to bx. From this, mod of y of t is equal to mod of x of t, which is less than or equal to bx. So we see that here if the input is bounded, the output is also bounded. From this, we see that the system is stable in BIBO sense. Now, let us look into another way of characterizing the systems, that is invertibility. A system is invertible if the output if the input x of t can be obtained from the output y of t using another system ti. That is, suppose there is a continuous time system which produces a output y of t for an input x of t. Now, if we are able to find another system ti or transformation ti using which we can get the input x of t from the output y of t, then we say that the system is invertible. Graphically, it can be written that so there is a system with transformation t which produces an output y of t for an input x of t. Now you pass the output y of t through another system of transformation ti to get x of t. Then we say that the system with transformation t is invertible, and the system with transformation ti is the inverse system of the given system. Mathematically, it can be written that the given transformation y of t is equal to transformation of x of t should be 1 1 and on 2 for the given system to be invertible. The same analogy can be extended to discrete time systems as well. Now let us consider some of the examples. Consider the system y of t is equal to 2 into x of t. This system is invertible as the input can be recovered from the obtained output using the transformation y of t is equal to x of t by 2. Now let us consider another system y of t is equal to square root of mod of x of t. This system is not invertible as x of t cannot be recovered for any given y of t or for any obtained y of t. This is mainly because of apps operation. Now let us consider another example. Y of t is equal to integral minus infinity to t x of t dt. Now this system is invertible as x of t can be as the output y of t can be passed through a system of transformation. Y of t is equal to dx by dt to get the input back. So now let us consider some of the problems related to invertibility. um, Suppose there is a system given as y of t is equal to 2 into x of t plus 3. We have to find if the system is invertible. So in this case, try to get an equation where x of t is on left hand side and y of t is on right hand side. So upon simplifying in the direction, we get x of t is equal to y of t minus 2 divided by 3. So for the given system, whatever we got is the invert system. So the given system is invertible and we also got the inverse system. Now let us consider another system. Y of t is equal to x square of t. We have to find if the system is invertible, and also we have to find the corresponding inverse system. In this case, we can recover x of t from y of t as x of t is equal to square plus or minus square root of y of t. But in this case, the problem is that we can't recover the sign information completely from the obtained y of t, and that's why it could be a positive sign or negative sign. From this, we see that the given system y of t is equal to x square of t is not invertible. This is mainly due to the ambiguity related to the sign. Now, let us consider the last example, that is y of t, sorry, another example, that is the given system is y of t is equal to mod of x of t. In this case, also, the given system is not invertible because of the loss of the sign information. So, given any system, by getting x of t towards the left hand side and y of t on right hand side, we can try getting the inverse system, and hence we can find if the system is invertible or not. Now let us consider another problem as related to invertibility of the systems. Suppose there is a system that is described as y of n is equal to e power x of n. We have to find if the system is invertible. We can r- simplify the given transformation such that the x of n is on left hand side and y of n is on right hand side, and it can be written as x of n is equal to log of y of n. From this, we see that the given system is invertible, and x of n is equal to log of y of n is the inverse system of the given system. Now, let us consider another system. Y of n is equal to x of n minus 2. We have to find if this system is invertible. On seeing the system, we can say that the inverse system of above can be x of n is equal to y of n plus 2. Let us consider this, simplify this by an example. Suppose x of 0, sorry, x of minus 2 is equal to 3. Now if you substitute n is equal to 0, y of 0 is equal to x of minus 2 is equal to 3. Now in the inverse system, if you substitute n is equal to minus 2, we get x of minus 2 is equal to, sorry, this should be 3. X of minus 2 equal to y of 0 equal to 3. So from this we see that using the given inverse system or the obtained inverse system, we are able to recover the signal back. From this we see that the given system is invertible. Now let us consider another system. Y of n is equal to n into x of n. We have to find if the system is invertible. On seeing the given system, we can see that x of n can be written as x of n is equal to y of n by n. So the input x of n can be recovered, but there is a problem for n is equal to 0. For n equal to 0, x of n would tend to infinity. Actually, in this case, the from the given y of n, x of n cannot be obtained. From this, we see that the given system is not invertible. Now, let us consider another system. Y of n is equal to f of integral minus infinity to, sorry, f of sigma m equal to minus infinity to n x of n, where f of x equal to 1 for mod x less than or equal to 1, otherwise it is 0. From this, we see that y of n is written as clip of, or rather say From this, we can see that y of n actually takes the sum of x of n, which is sigma m equal to minus infinity to n x of n. Based on the obtained summation, it gives the values as either 1 or 0. Now, from this 1 and 0, we can't get x of n back from, say, y of n, that is 1 or 0. From this, we see that the given system is not invertible. So if we see y of n is written as f of absum, which is written here, but this final value that we get for y of n would be either 1 or 0. But from this 1 or 0, which are values of y of n, we can't recover x of n back. From this, we can say that the given system is not invertible. Now let us consider another system, that is y of t is equal to t into x of t. This is for t not equal to 0, and it is x of t. This is for t equal to 0. From this, we can see that x of t can be written as x of t equal to y of t by t for t not equal to 0, and it can be written as y of t. This is for t equal to 0. From this, we see that the obtained y of t from the obtained y of t, we can get x of t back for any t or for every t. So we see that the given system is invertible and the inverse system is as marked.